How did the cosmos come to be? What purpose does life serve? What occurs to us once we pass away? And how many people would it take for a Tyrannosaurus rex to consume the necessary number of calories each day? The answers to the first three of your queries are not included in this book summary, but it just might. The renowned webcomic XKCD was created by scientist and former NASA employee Randall Munroe. Additionally, he holds that no inquiry is ever foolish. Since 2012, Munroe has invited blog readers to submit the silliest hypothetical questions they can think of, and he has been responding to them as seriously and scientifically as he can. Munroe's responses to some of the most bizarre questions he has ever been asked are collected in this audiobook. Yep, just like the Tyrannosaurus Rex story. The answer, incidentally, is roughly equal to one 10-year-old child or half an adult. Conversely, if there is a McDonald's nearby and you want to prevent being devoured by a T-Rex, about 80 Big Macs. What would occur if Jupiter were reduced to a house's size and positioned in a residential street? Do you like to hear the positive or negative news first? Let's start with the good news. Jupiter has a density that is similar to that of water. Jupiter would only weigh 2,500 tons if it were the size of a home, or, let's say, around 50 feet broad. In other words, your new neighbor isn't going to create a black hole and mess with your gravity. Jupiter is not truly formed of water, which is bad news. Jupiter used to be a large diffuse cloud of gas floating through space before it became, well, Jupiter. The gas cloud eventually collapsed in on itself due to gravity. Compressing gas causes it to heat up. Really hot. Similar to Earth, Jupiter is made up of a hot center that is covered by a thin, cool surface layer. Tens of thousands of degrees hot, to be precise. Jupiter's interior yearns to expand, as does the interior of anything that is intensely hot and tightly packed. It doesn't, but only because that impulse is resisted by its own extremely powerful gravitational forces. When Jupiter is shrunk to the size of a home, its powerful gravitational pull is eliminated. Thus, this is what would occur. Jupiter would swiftly grow outside in a fiery inferno. That will have a significant negative effect on the property prices in your street because it will be completely destroyed. Your entire neighborhood is actually destroyed. Okay, let's end on a positive note anyhow. This blast should be reasonably contained. Jupiter's molten hot core will swiftly cool if it is not crushed tightly. And Jupiter will revert to its former state, which will be as hazy gas clouds floating through space. Which nation would control the majority of the cosmos if the borders of the nations of Earth reached the stars? Australia would be recognized not only as the home of kangaroos and the Hemsworth brothers but also as the galactic ruler if every nation's territory reached infinity skyward. How does that function? Since the Earth rotates, every 24 hours, different nations would actually control different portions of the galaxy's airspace. Yet, southern hemisphere nations like Australia have an unfair edge in this situation. The southern hemisphere is favorably inclined toward the galaxy's core since the North Pole points away from the galactic center. Australia, South Africa, Lesotho, Brazil, Argentina, and Chile's airspace would circle around the galaxy's core, which is a supermassive black hole. Australian airspace would be able to claim more of the galaxy than any other nation once the galaxy's center was located there. But there is still something left for the northern hemisphere. It is inclined toward the outer galactic disk, where there is a ton more exciting activity taking place. For instance, a black hole called Cygnus X-1 would fly over North Carolina's airspace as the galaxy's core crosses the Pacific Ocean in the southern hemisphere. Claiming a supergiant, star-devouring black hole as part of your airspace when Cygnus X-1 is actively consuming a supergiant star is pretty metal. The galaxy's outer disk is home to millions more planetary systems in addition to Cygnus X-1. In the same way that the star 47 Ursae Majoris, which is known to have 3 planets orbiting it, would regularly pass over U.S. airspace. Let's assume that even one of those worlds has life. Any crimes committed on one of those three worlds would officially come under the legal authority of the state of New Jersey for 12 minutes out of every 24. Of course, by the time legal action was taken, the statute of limitations would have most certainly run out because it would take 40 light years to travel from 47 Ursi Majoris to a district court in New Jersey. How many people would it take to erect Rome in a single day? First things first, we are all familiar with this adage. Without a doubt, Rome was not constructed in a day. But is it possible? The assumption in the question is that just adding more workers would hasten the process. Anyone who has attempted to organize a gathering for 3 or more people will be able to tell you that this is almost always false. More attendees can often lead to greater issues. And in the case of constructing Rome in a single day, those challenges include, but are not limited to, organizing and training a sizable workforce to carry out specialized construction work while preventing bottlenecks as sizable crowds of laborers move throughout the relatively small city, and coordinating supply chains to deliver sizable loads of building materials when and where they are required. But hey, let's continue with the query. Daniel M. Chan, a civil engineer, has developed a clever formula for calculating the length of time it will take to complete a building project depending on its cost and size. Let's assume, as a very preliminary estimation, that Rome's real estate is worth $150 billion. And let's assume that the construction costs equal around 60% of that amount. $90 billion, then. Chan calculated that the construction of Rome would require 10 to 15 years. Far from a day. But let's attempt to accelerate this. Rome would require approximately 2 billion hours of effort to complete, according to the author's calculation. In other words, it would take less than 15 minutes to bring it down if 8 billion people were working. Well, so this strategy might work for simpler construction tasks like creating roads and typical structures. Rome, however, is home to many magnificent works of art and architecture, such as the Sistine Chapel's ceiling. When calculating how many people it would take to create Rome in a day, how can we account for that? The beautiful frescoes that cover the entire 523 square meters of the Sistine Chapel ceiling were painted by renowned Renaissance artist Michelangelo over the course of 4 years. This translates to around 1 square meter every 16 hours. 1,285 square kilometers make up Rome. Hence, if Michelangelo had built Rome at his painstaking pace, it would have taken 20 billion years. The task could be completed in around 2.5 hours if 8 billion workers contributed equally. So there you have it, 8 billion individuals could construct Rome in anywhere from 15 to 2.5 hours. The next query. After building Rome in less than a day, how much spaghetti is required to give 8 billion people lunch? What would it be like to stand at the lowest point of the ocean if you were inside a completely impermeable glass tube that extended from the ocean's surface to its bottom? Whether or if you bring a great, thick sweater and a torch with long-life batteries with you to the ocean's bottom will determine the answer to that query. You would be 3 times deeper below sea level than the deepest mines in the world if your completely indestructible glass tube ran from above the sea's surface all the way down to the Mariana Trench's greatest depths. In a mine, the temperature rises as you descend further. This is due to the fact that mines are bored into rocks, which become hotter as they approach the Earth's core. Yet, the temperature at the ocean's depths is just above freezing. Hence, you will experience cold. The Mariana Trench floor, one of the least visited places on Earth, will be visible, so that's a positive. I'm joking. But when the sun directly illuminates the opening of your glass tube, which will happen exactly twice a year, around April 20th and August 23rd, you won't be able to see much at all. Another 6 months of complete darkness follow. You should probably enter your elevator and exit unless that sounds appealing. You do realize that your glass tube is completely unbreakable, right? That lack of response will be interpreted as a negative. At this point, you could always make a hole in the glass tube side to allow water to enter, which would then lift you beyond sea level. But, be sure to keep your distance from the hole itself. A saltwater jet that has been supercharged will rush through that hole when it opens. In fact, It's not the best idea to merely let a lot of water flood into the bottom of your tube even if you could manage to stand away from the hole. The water would rush upward in a column with a 1.3 Mach value. You wouldn't be able to withstand the impact if you attempted to ride this water column upward. Your best option would be to slowly and carefully open a tap at the bottom of the tube to allow water to flow through. It would only be safe to fully open the tube's bottom and allow more seawater to flood in when your tube has accumulated 1 or 2 kilometers of seawater. You would be back above sea level in less than a minute, traveling at a speed of 500 miles per hour on a massive fountain of freezing water, assuming you had a gigantic plunger on standby to keep all the water safely underneath you. Well, let's go back and update that packing list. Sweater, flame, faucet, enormous plunger. You may proceed now. Is it possible to eat a cloud? A cloud is a mixture of water and air. Water is also edible, right? Or at least drinkable. Theoretically, nothing should be able to prevent someone from eating a cloud, apart from, common sense, having better things to do with one's time, and the difficulties in getting a cumulonimbus to remain still on your plate. But the issue is as follows. It's going to be hard to absorb unless you could figure out a technique to press the air out of the cloud before you started eating it. Imagine putting a bit of cloud in your mouth. The water it holds can be consumed. Yet, you'll still have an unusually huge amount of air inside of you. Your body will have to release the trapped air, which it will do by burping. The problem is that once air is inside your body, it starts to absorb moisture. Your pleasant, warm, wet air will condense when it comes into contact with the cool outside air. And create clouds. Extra cloud. You won't have time to finish the cloud before you burp it up. Imagine being able to extract the water from a cloud by either putting it through an extremely fine filter or ionizing the water drops and removing them with an electrical charge. You would undoubtedly be able to consume a smaller cloud in such scenario. The amount of water in a cloud the size of a small house would be between 2 and 3 liters, which just so happens to be the most liquid the average human stomach can bear at one time. There isn't any other cuisine that you could eat in house-sized portions. Even foods with extremely low densities, such as cotton candy, are more denser than clouds. At most, you could consume 1 cubic foot of cotton candy in a single sitting. On the plus side, it may taste better than the typical cumulonimbus. If a snowball were rolled from the summit to the base of Mount Everest, how big would it get? Snowballs can only enlarge by rolling through moist, clingy snow that sticks to their surface. The snow on Mount Everest is soft and dry. Hence, even if you were to roll a snowball all the way down empty Everest from the summit, it would remain roughly the same size as when you started. How big would your snowball get if empty Everest were blanketed in moist, sticky snow? A snowball does, in fact, accumulate more snow the bigger it gets. Thus it seems sense that a snowball will expand more quickly the longer it is rolling and gathering snow. After all, if the term snowballed weren't entirely correct, we wouldn't use it to describe exponential development, now would we? Yes, in regards to that. A snowball's surface area increases as it accumulates more snow. A snowball's growth will actually slow the longer it rolls since each fresh patch of snow has to cover a lot more ground. You're not using the term correctly unless you're referring to anything that begins to grow exponentially before immediately slowing down. There are many flat glacial troughs along the route from the peak of Mount Everest to base camp, where a snowball would stop rolling, so it's not all downward slope. The 3 main slopes of the mountains, however, each have dips of around 5 kilometers. A snowball moving down one of these slopes could theoretically eventually expand to reach between 10 and 20 meters broad. In theory, but not in practice. A snowball wouldn't actually grow wider than a few meters before it would crumble under its own weight. It would then crumble into smaller snowballs, each of which would begin to grow until they, too, crumbled into smaller snowballs, each of which would begin to expand, and so on. In other words, a snowball wouldn't get very big if you tried to roll it from the summit to the base of Mount Everest. On the other side, the avalanche you might start could be rather large. Math doesn't have to be boring, and science doesn't have to be serious. It's a terrific method to exercise your analytical thinking while also having fun to stretch your brain by attempting to solve absurd puzzles.